So Shiva, can you see the screen?
Yes, sir.
Okay, thank you. So in the last class, we're actually trying to derive the loss function for variational autoencoders. We're in the process of deriving. As I told, the derivation may not be important for your actual preparation, but it's only to tell you the steps that people have followed to come up with this loss function. Okay, now let us see. Um, yeah. Now we'll continue this. We came up with this last equation and then we will try to further simplify it. Now what I do is I'll apply minus on both sides. This is my left hand side. This is my right hand side. What I do is I'll apply minus on both sides of my equation. Then this thing will changes like this. The LHS will changes log of P of x minus dKL. Okay. So KL diverges between what? Q phi of z given x. I have not written here, but I'm just writing here. Okay. So P of theta z given x. This is my R left LHS. Now let me also apply minus sign on the RHS part. Then it will be Ez log Q phi. Just a second. So it is okay, fine. Log theta. Then it would be actually okay, it should be plus z. Okay, fine. Yeah. So log P theta x given z minus Ez log Q phi z given x minus log of P theta of z. So what we do is, if you actually see this as Ez log of P theta x given z, this is as it is I'm writing, okay. And if you see this guy, this is basically again KL divergence between what? dKL of Q phi z given x to P of z. Sir, what are you doing here? Just trying to come up with some simplification, but what is happening here? See, this conclusion is important. See, finally, after simplifying, we got this particular thing. Earlier, if you see, we started with the dKL between what? The TKL is between ZX and ZX. Okay, because we're trying to estimate the P theta of Z given X with Q theta of Z given X. Now, we actually simplified that to these two terms. This is my first term and this is my second term. Now, if I can say that this is tractable, then definitely it is easy to calculate. Now, firstly, what I do is the first term is definitely tractable. So before I show you it's tractable, let me write the loss function. Any loss function, you know that here I want to minimize the objective function. So because it's a loss, so I'll say that I want to minimize my objective function. I want to minimize my objective function. So now what I do is I just apply again just minus to the entire term because I want this entire term to be minimized, not maximized. Okay. Now what I do is I just put minus term in the entire equation that I have and just write the same thing again. That's all. Okay. Now, if you see, KL divergence initially has Q z given x and P z given x, but see now we have one conditional probability Q z given x, but we don't have a conditional probability in the other side. Actually, what is P of z? This P of z is a prior probability of our latent space. Since this is prior probability and known from the previous instances, then definitely what you have to do is you need to ensure that your estimated or inferred Q phi of z given x is very, very close to P of z. Okay, you need to reduce this distance so that your inferred will be very, very close to the P of Z distribution. Okay. So now actually, if you see the first term, again, I'll come back to the second term again. Let us see the first term now. This term. Actually, this term is actually called as reconstruction term. Reconstruction term, because this is P of X given Z is the decoder term. Once I have Z, I'll use the distribution P of X given Z to get the X dash. So it's actually reconstruction. Even though I say reconstruction, I'm not intended to say that you will get the same image back, but it's actually some other reconstructed image, which is very, very different and realistic from the input image. Now, since this, that's the reason it's called reconstruction likelihood or log deconstruction log likelihood. What we do is, again, what is the distribution of this? Because it's a probability distribution, right? What is the probability distribution of this? So the probability distribution for this is actually Gaussian distribution. Sir, how do you know this is Gaussian distribution? This again, I'm putting a restriction because I don't want my log P of X given Z should be following some other distribution. I'm restricting my probability distribution at the decoder side to this distribution. Sir, you may ask, why, sir? Why Gaussian distribution? Because you see, this complete things work on the assumptions of the distributions, and we cannot assume any distribution just like that. The only thumb rule whenever you're estimating any distribution, you start with a Gaussian distribution and you slowly transform to the target distribution. So that's a general thumb rule that we follow in the probability. Similarly, the prior probability, I restricted that the prior probability should follow a standard normal distribution with mean 0 and unit variance 1. That means I'm telling my system, Arey Baba, you have input image X. I don't know what you'll do. Whatever the jet that you're trying to extract from X, the encoder extracts jet from X, whatever you're extracting, the jet has to follow normal distribution, standard normal distribution. Ensure that you understand the X in that way only. The extracted feature should follow. That means I'm restricting my jet to follow that. Okay, because what happens if it generates its own distribution, it is difficult for us to actually make it a tractable one. Okay, so that's the reason people assume that the prior probability the jet should follow a standard normal distribution with unit variance and mean 0. Okay, now since my jet is a standard normal distribution, the samples extracted from the standard normal distribution can also be a Gaussian distribution, because I cannot have a very drastic change. That means I'm restricting my jet, I'm restricting my decoder, and finally getting X bar. That means whether I restrict or not, that's a different story, because see, whether I restrict to Gaussian or some other distribution doesn't matter, guys. What matters, the weights matter. Because for example, I had restricted my latent space to follow some distribution. With this distribution, I have sampled certain instances or certain values out of this latent representation, and the latent representation is using some weights, and these weights in conjunction with that latent space would give me some image X dash, If this X dash is not X as expected, it was unrealistic. Assume that it was unrealistic. Then what do? You'll not change the distribution, but you'll change the weights. Maybe these weights are not optimal to generate a realistic image. I update these weights. Still, assume that if still after changing a lot of things also, we are not done with we are not actually able to get satisfactory results, then there will be weights 5. Then you will update these weights, but you will not change the distribution. You restrict your model to ensure that the latent space follows standard normal distribution, so that your model will be keep on trying the changes in the weights, not in distribution context. Okay, so now after putting these many constraints, the flexibility is also reduced. Once you have a flexibility, once you reduce the flexibility, what happens? You're trying to reduce the chances of overfitting. So simply, people do not keep the restrictions. If they don't keep the restrictions, then definitely with a high flexibility, it gets overtrained and it ends up at getting like bad results in the deployment part that I don't want. That's the reason I'm putting as many restrictions as possible and trying to change only the weights point of view. Now, so this is actually a log likelihood or reconstruction part of my loss function. But actually, I say that this is to be precisely called as squared reconstruction loss. This particular first term is called squared reconstruction loss. So what do I mean by squared, or how it's called squared reconstruction loss? What I assumed that this particular guy follows normal distribution. You know already, guys, the probability density function for a normal distribution actually gives, like, you know, this formula from your, I think, 9th class or 10th class people studied this. Even in your ADA courses and other courses we have seen this. So it's actually 2 pi of x. So different variants do exist for this. I'm writing one variant. I'm just writing the probability density function of p theta given z. That's all. Okay. Now what I do is I'll just apply log on both sides, because what I want log of, change the color. I want log of p theta of x given z. So I just apply log on both sides for the probability density function in the context of Gaussian distribution. So log of p theta of x given z. I'm not trying to evaluate everything after log. So this is a constant term. Okay, I'll not do that. So I'll see the proportion to which it is proportionate, because again this is also constant too. So I'll just remove that and directly say, because when I apply log, this exponent goes. So it is mu theta of z given transpose and covariance theta inverse z x minus mu theta of z. Okay, so this is just directly proportional. Since these lead to a scalar value, I just multiply these guys. Then it is actually mu theta of z whole square. So now that's the reason people call the first term as not just a reconstruction, log reconstruction likelihood. They also call this first term as reconstruction, squared reconstruction loss, squared reconstruction error. Why squared reconstruction error? It's a squared. Why it's called reconstruction? Because this is my original x and this is my mean. This is my mean of the latent space. Okay, so if I could find the Prior distribution jet, I already told the Prior distribution jet follows a standard normal distribution, and x may follow standard normal distribution. In most of the cases it will not follow. Then when you take the difference between x and its mean, definitely the difference will be very, very high and the error is very, very high, and then you will be able to get very high loss. Then in that case what you do, you update the weights theta such that this standard normal distribution will change in such a way that it actually represents a latent feature space which follows this particular distribution. Okay, so it's an iterative process, but one thing you need to remember, it is easy for me to transform standard normal distribution to any other distribution. That's the reason I start with standard normal distribution. Okay, fine. So the first term is basically a squared error or squared reconstruction loss. So with this, we are done with the first term. Now let us see the second term. Second term, change the color. Yeah. What is second term here? This is my second term. Where is that? Yeah. This is my second term. It's basically KL divergence. Now let us see what exactly the second term is all about. DKL of QZ given X between P of Z. The beautifully what we have done is, if both are conditional probabilities, we could not infer anything. We, after simplification, we could eliminate one conditional probability, and this one is a prior probability that I assumed as a standard normal distribution, but over a period of time that will get transformed to my original X distribution in the context of latent feature space. Okay, now this is the main theme, perfectly fine. Now, what is this? This guy is actually standard normal distribution with zero mean and variance as 1, perfectly fine. And I also told this will assume as a Gaussian distribution or a normal. It's not a standard normal distribution, it's a Gaussian distribution. So with some mu of X and covariance of X. Okay, this is actually covariance symbol. Okay, this is standard normal distribution and this is normal Gaussian distribution. It's not standard one. Now, actually, KL divergence between two normal distributions. KL divergence between two normal distributions is actually 1 by 2 into of trace sigma, as not sigma, it's actually covariance. So X plus mu, I have to write this phi, so always phi of X transpose, and you have mu phi of X minus K minus log the determinant of mu phi of X. See, again, you'll get literally shocked here. Sir, what is this? What is this? What is happening here? Guys, actually, I already told that we'll be able to calculate the difference between two distributions, but earlier we could not calculate the difference because earlier here it used to be a conditional probability, then it's not possible. And now that was now converted to one normal probability, which is already known to us. We assume that it's not standard normal distribution. Now, if I just see, if I just want to simplify it further, if you just search in internet also, you get this KL divergence between two normal distributions. KL divergence between, if you want to find out the distance between two normal distributions, this is the equation. No, sir, we want a proof. If you really want, I'll send a recorded video, but it's not important. But I'll see whatever the left topic that was there in our syllabus. Along with that, maybe if you want, I'll upload this proof. Okay, maybe separately I'll upload so that if you really want this, you can go with it. Okay, but as of now, again, mostly I'll upload it now because I'll not be satisfactory if I don't upload, because like I don't want you to remember. Okay, there will be like 10 to 15 minutes of proof, 10 minutes around, so I'll upload it. Okay, but as of now, you just think that after simplification you got this particular term. Now what we do is we further simplify this. Okay, so slowly we're adding it. We initially came up with this term and we assumed both these guys as normal distribution, then simplified with certain maybe 10 to 15 steps, and I got this. Okay, I'm not mentioning that 15 steps now, 10 to 15 steps, that we will see later, because if I start telling that, it will take a lot of time. And this proof is not greatly important for you, but I'll definitely say because I don't want you to by heart. Okay, let us continue this proof from the above step. It's 1 by 2. What it was, this is trace. I think many of you know about trace. Trace is actually sum of diagonal elements. Trace is basically sum of diagonal elements. Assume that I have k elements in the diagonal, then it would be, I'll remove that trace and this sum over the k elements. Okay, and this is covariance. See, maybe you need to be, if people just confused with this is summation, this is covariance, maybe small letter I'll write. This is covariance of X. Okay, and then this is again a scalar value. Okay, it's actually a mean, so I just say that it's over the k, because over k values only I calculated the mean, so whether I write summation or not doesn't make any difference. So it's mu phi. So since I have two scalar values, I can take a square of both. It is actually X minus actually k. So can I say, how do I get k? If I add k once, if I add k once, I would get k. And again here, this is not anything. This is actually determinant. This is actually a determinant. The determinant is actually a product of the diagonal elements, right? So actually, the log of product of the diagonal elements. So product of k covariance of X. Okay, so I want to remove that determinant. That's the reason I put this product term. Okay, so now what I do further is 1 by 2. I'll just write the same thing here. Okay, log, I'll write, I think, okay, because I want to rewrite it again and again because it's time waste. So what I do is I just say this is as it is, this is also as it is, this is also as it is. Now let us take this particular one. It's actually in the form of log AB. We can write as log A minus, sorry, let's log AB format. We can say log A plus log B, right? So we'll try to do that and see how the things will flow. Am I doing something wrong here? Okay, fine. Yeah. So this is actually product of terms. This is product of terms. Now you are trying to write this as sum of both the terms. That is nothing but here. What is that? Here it is minus log sigma of phi x minus, what's is actually minus sigma of over k log of covariance of phi given x. So I converted the product of these terms to the sum of the terms, which is actually basic logarithm property. Now why I have to do like this? Because I have summation here, I have summation here, I have summation here, I also have summation. I just want to keep all this as common. So it's 1 by 2. And then I have summation common over k. And rest of the terms I'm just writing sigma of phi of x plus mu square phi of x minus 1 minus log covariance of phi of x. Okay, now actually what people have done is, while they're actually deriving this, they found out that instead of log terms, exponent based, so like an exponent based term is giving more stable results for numerical stability. What they've done is they've applied exponent and try to remove the logarithm. It's only for the stability purpose. No sir, I'll keep it like that, you can keep it like that, no problem. But they have found out it's not so stable, so they've just applied exponent, that's all. So sigma of k, I'm just applying exponent. So exponent of covariance of phi given x plus, okay, so I did not apply to all the terms, only they applied for the covariance term, okay, because like the other terms did not do it, they did not find any instability there. And minus 1 minus, again they applied exponent here, and the other one will go off, the logarithm will go off, and finally you have sigma phi of x, not sigma, it's actually covariance. Now finally, what is the final expression we have? This is the final expression. Now, if you see, combining the initial first term and above second term, we get the final loss function. This is the second term I simplified now. From the second term, from the KL divergence, this is the one. Now, actually, let's copy this and paste here. This is the second term, okay, of my loss function. What is the first term? What is the first term? First term is actually Ez sampled over q phi of z given x. So we have a logarithm of p theta of x given z. This I already told, this is actually squared reconstruction loss. Squared reconstruction loss. And this is the KL divergence simplified version between two normal distributions. Two normal distributions. So this is actually simplified loss function. Instead, I could say that, okay, this is a variation autoencoder architecture. This is the final loss function. I could say directly this, but I did not tell you because I want you to understand what is happening to get with this final equation. Okay, now if everything is tractable, the squared reconstruction loss that I've calculated before, because P of x given z follows normal distribution and probability density function, and it's actually squared reconstruction loss. Definitely it is calculated, it's tractable and you can calculate it, each and every term in that. Similar, the KL divergence between two normal distributions also, we calculated two, it's actually just a covariance and the mean. Just a covariance and the mean, then you'll get the KL divergence between two normal distributions. That's all. As simple as that. As simple as that. Okay, so that's the reason. If this is my loss function, this loss function has to be minimized. Till that time, the adjustments will be done. What adjustments? I already told, we have taken the inference of, we estimated P of Z given X using Q of Z given X. Okay, so if this assumption was not great and this distance is very high and this distance is very high, then I would get very high loss. Then what I have to do, these 5 weights has to be adjusted so that over a period of time you would get minimal loss. So it's very simple idea, Nana. Earlier we used to assume certain values of the weights. The certain values of the weights are changed, only the weights used to get changed, weights and biases used to get changed based on the loss function. Now, these 5 along with the 5 set of weights, the distributions also will get transformed such that the loss is minimal. So that's the main theme of variation rate autoencoder loss function. Now, once I have a minimal loss, what is the next step? I have to do back propagation. Now, back propagation, again, you need to update the weights. Again, whenever you're trying to update, then what are the weights that I have? Weights with respect to theta, weights with respect to phi. Okay, so you need to run some gradient descent. Maybe assume that my optimal weights are phi theta, theta star and phi star. These are my optimal weights. Now I need to apply some gradient descent over the loss function, which is actually having theta and phi parameters. And similarly, I have to apply gradient descent with respect to phi on the loss function theta and phi, which we have just derived. Just now we derived the function with respect to theta, you take the derivative, with respect to phi, you take the derivative, and you ensure that both of them gets the optimal weights. So, okay, so these are theta star is the ideal weights and phi star is also ideal weights with respect to P. This is decoder optimal weights and this is encoder optimal weights. Okay, so this is the main theme of entire variation autoencoders. Again, guys, if you don't understand the derivation part, you don't need to worry. You don't need to worry at all. But only thing you have to remember is the loss function that we have derived. The loss function that we have derived has 2 parts. The first part is squared error reconstruction, or maybe to be precise, let us squared reconstruction error, which is actually trying to minimize the distance between the x and the mean of z that we have taken as standard normal distribution, and then trying to find KL divergence between 2 normal distributions. Okay, and these are modeled with respect to theta and phi, and these gets changed such that the loss is minimal. Okay, now why we have to take KL divergence? What happens if KL divergence is not there? Only I've taken this squared reconstruction error where I'm trying to minimize the x distribution and the z distribution. What is square reconstruction error? This only, I told. So you're trying to minimize the distribution differences between the input x and as well as the latent feature space z. Then what happens if this term is not there? See, KL divergence actually acts like a regularizer. What is regularizer? You add some noise. Kind of noise, so that it will not overtrain. Okay. Similarly, here also, why it's kind of noise, why it's kind of regularizer? Because I'm putting a lot of restrictions in this. Arey Baba, my original distribution is P of Z given X. Unfortunately, you are not capable person to find of P Z given X. Then you're putting a constraint that let me estimate with Q Z given X. Again, this is definitely some constraint. Again, you're telling that this is you need to find out the distance between this guy and this guy. You're not able to estimate the distance. Then you estimated the distance between QZ given X with P of Z. In P of Z also, you're estimating that it's a standard normal distribution. Again, one more constraint. Whenever you're putting many constraints and still asking the system to get minimal loss, system will not have a lot of freedom in just updating all the possible combinations. Then it will not overfit. Okay, so what happens is at the end of the day, you will not be able to have a chance of overfitting when you're trying to go for this variation autoencoder in terms of KL divergence also. Okay, this is the main theme behind the entire invention. Now, after this, what else we have? So we are done with the architecture, we are done with the loss, and we're done with the back propagation. See, whenever you're doing back propagation with respect to theta, with respect to phi, you may sometimes need to do reparameterization. I'm not going with that. That's not required as of now. Reparameterize in the sense, I think variable shift is a concept in probability and statistics. So that sort of reparameterization may be required. Some linear transformations should be done. Because, for example, if I want to take the derivative of something, maybe on, how do I put it in a simple terms? Okay, so while you're actually doing the while you're actually doing the gradient descent, what happens is you'll get a term where you have some expectation over something, but for example, I'm trying to do the derivative of theta, and theta may be there in the entire expectation. It was not there in the inside term. Then you need to do some reparameterization, introduce some linear transformation to ensure that you have theta even in the inside parameters, so that your gradient also would flow very nicely. So all these things, I think if you know about reparameterization and probability, it would be fine. Otherwise, also no problem. It's just a simple step. It's like a 2-line step. Otherwise, the rest, ignoring the reparameterization, changing and introducing some linear transformation, rest of the gradient descent is 100% the same as previous. So with this, we are done with the architecture part, the loss function part, and just introduce the back propagation. And we said that except reparameterization, remaining back propagation algorithm remains same. So we are done with variational autoencoder. And the last topic that was there in our course is actually the other generative models. I already told you we have two generative models. One is variational autoencoder and other one is GANS, generative adversarial network. Okay, we'll see that now. Generative adversarial network, and short, they're very popular, called as GANS. Okay, now what's the main theme of GANS? Actually, they're also used to generate new output images when compared with input images. Okay, and what are the applications that I told for image to image translation, text to image translation? The similar applications are solved by GANs. Then why two guys are required? Why variation autoencoders and why GANs for the same purpose? Actually, both of them follow a different approach, completely different approach to generate new stuff. The GANs actually, the other name of GANs is actually two-player. It's a two-player non-cooperative game. The other name, the unofficial term for this entire thing is actually two-player non-cooperative game. Why it is actually a two-player non-cooperative game, I'll just tell you guys. So I'll start with a very simple example so that you'll understand the entire stuff in one line. So basically assume that I have I have a short image. Maybe I'll just draw that, even though I'm not good at drawing. Okay, this is a shirt. Assume that this is a shirt. Okay. Now, like this, I have multiple shirts. Shirt 1, shirt 2, shirt 3, shirt 4, like that in my data set. I think many of you know about MNIST fashion data set, right? Not only digits, it's a fashion data set we have. So assume that I'm a designer and my boss asked me to come up with new designs. And I've taken all the existing designs in the market. Somehow I could not come up with a new design. So let me take the help of the system and then generate new images. And I impress my boss automatically without me putting a lot of effort. That's a good idea, right? Now, you will generate this. You'll give this input to a CNN model. Your entire image, your entire data set, fashion data set, where it contains a lot of shirts and other things, you'll give to CNN. Let CNN, what it do, CNN basically classifies. These are all original images, right? Original images. And since we are giving original images, I don't want to my system to release shirt or pant because all are shirts. I don't want it to tell the system like cotton shirt or non-cotton shirt or linen. I don't want that. I just want only one output. That is, I just want to know whether it is actually a genuine picture or like an original shirt or not. Okay. If it is a non-original shirt, then maybe what I do is I'll also generate some faked images. I generated some faked images. Now, these faked images also will be sent to CNN. And whenever I pass this faked shirt, I want my CNN to say 0 because this is not the original shirt photo. It was some artificially generated one. So I wanted 0. Okay. So this is perfectly fine. No, sir, we are not convinced about this. Then let me tell you. Actually, I initially thought to tell you that example, but it is illegally not to tell that. Actually, it's not good to tell that example, but I'll still tell because I want you to understand well. Assume that I want to prepare a fake note. I want to prepare some X person want to create fake notes. Now, how does it do first? Firstly, he will take all original notes, original 2000 rupees notes, all original 2000 rupees notes. And you know, guys, there are systems in the bank. Once you put that note in the system will say it's a fake or genuine 2000 rupees or 1000 rupees, whatever. Okay. So assume that you prepared a system, a deep learning system, where it scans your note and tells whether it's genuine or a fake image, faked note. Okay, perfect. Now, but if your model only knows about the fake, about the fake, sorry, about the genuine, only if the system knows about the genuine, it cannot actually classify the faked ones. Now, I want fake notes also. I want fake notes also, but from where I get it? Should I go to police station and take the old cases and old criminals and their submitted case, all submitted evidences, all that things? No, I don't want. Somehow what I do is I'll also generate these fake notes artificially. Let me generate the fake notes artificially. I don't know how the fake notes will be. Okay, but I'll generate. Now, assume that I think you on the other day somebody is telling me that the movie Allu Arjun movie that was recently released. That person is telling me, sir, unnecessarily a smuggler has been shown as a hero, as a heroic role as a smuggler has been shown. That means it's a bad character, but he has been projected as a hero. That's fine. It's a story. It's just a movie. Now, in this case, also, our hero is not this original notes. Our hero is a fake note guy. Okay. So now I want my person who is creating fake notes to fool the police. Who is police here? Police here. CNN. Now, once this fake note guy gives a fake note to the police or a bank person, the police or the bank person should be correctly identifying whether it's a fake note or a genuine note. Now, as a fake note person who is trying to make fake notes, what I expect if I prepare a fake note, this is genuine note and this is fake note. Now, if I start sending a lot of details to my CNN, assume that the police is there and the police actually getting trained to detect the original currency and the faked currency. Then tomorrow when you supply a new currency, police will be able to tell whether it's the original one or a faked one. Okay. Now, in this case, what police expects? Police wants if original cent are 50, faked cent are 50, he want all original to be classified, original to be classified as 50. All originals he should classify and all faked also he should classify. That means he should be able to classify or identify what is original and what is fake in 100% cases. That's his expectation. Whether he does it or not is secondary. But what is the expectation of the person who is actually faking the notes? He will generate a fake note that will be given to the police. And what is the expectation? Expectation is he wants the police to classify it as a one. That means he want his fake note to be classified as a real note. That is his expectation. Okay, is this entire case study fine? Basically, we are having a police that detects the original notes and the fake notes. Original notes, if I sent, I want it to be 1 and the fake notes to be classified as 0. Now, how do I get fake notes is a second story, but this is the one I want. But here, putting all these terminologies into the network part, actually what we do is we will have a network called discriminator network. Discriminator network would get all the images, original note images, all 2000, maybe you take in 2000 original note images. Now, actually, I also need to supply fake notes. From where I'll get fake notes? I will get it from generator G. Some generator. See, what is generator? Generator is some network, some CN network. What is discriminator? Discriminator is also a network. Generator, discriminator is very, very important words. That's the reason, since our hero is actually generator, not discriminator, it's called generative adversarial network. Okay, now see, now this generator responsibility is to generate fake notes in such a way that he has to fool the discriminator. Fake notes will always have 0 label, but generator don't want his fake image to be predicted as 0. Instead, the generator wants the discriminator to classify his fake notes as real. That is nothing but 1. Okay, so now the question is, how do the generator or the thief or the fake note person who is making fake notes can fool the discriminator? Unless until he is generating the fake notes in a very smart way, he cannot fool the police or the discriminator, right? But how does he do? That's very important. Here, do you know that? I don't know many of you know it or not. Actually, many of the people who are actually doing this fake note business are being caught many times. They can't fool the government. Reason is there are a lot of rules now. If you take a 1 rupee, like a 2000 rupee note, there will be some like a tag here. There will be something. I somehow that the different distinguishable parameters that is almost hidden inside the note. I heard somewhere there are around 180 markings that are detected by the systems to say whether it's fake or genuine. But do the people who are actually making it do know that? No, not at all. Not at all. Maybe the persons who are dedicated for this, or maybe the systems can do this, but as the fake, as a thief, I cannot do it. We can never do that. Okay. So that means the generator is not aware. The generator is not aware of all the patterns that makes his note a real. But so what he does is start with some noisy data. He just take some noise pixels, some noise distribution. Now from this noise distribution, he samples, the generator samples and generates some fake note. Now this, since he started with random noise, and if this fake note is given to the discriminator, in the first epoch, he classifies, definitely discriminator can easily identify because this fake note is just maybe a color printer note, that's all, but it doesn't have any patterns. Then in second epoch, the generator will send another image. Again, it can be easily classified by discriminator as fake. Again, third fake, easily detected. Fourth fake, easily detected. Then actually, the generator is worried actually. Oh my God, I sent 4 nodes. 4 nodes are classified as fake. That means my fake node generation is very bad. So somehow I should make it very intelligent so that the discriminator should not classify my image as fake. It should classify my image as real. So now, how does it possible? How can we achieve this? So actually, for this, people have solved this problem in various ways. Now we'll see one by one. First, let us see the discriminator and the generator. Okay, no, it's basically, I told now, it's a 2-player non-cooperative game. 2-player non-cooperative game. So here I have 2 players, generator and discriminator. Generator and discriminator. Discriminator responsibility is to generate or classify, not generator. Discriminator responsibility is to classify the real image as 1 and the fake image as 0. But generator will not make it happen. Generator image is always fake, but when it is supplied to discriminator, the generator wants 1 to be printed, not 0. till that point, the generator waits, keeps on updating, keeps on waiting, updating, keeps on updating. You understood? Generator and discriminator networks are basically CNN networks. So discriminator will keep on predicting 101010, but generator keep on updating its weights till the point the discriminator could not identify the fake nodes as fake. It should classify the fake node as real. That's the main theme. But now the question is, I started with a random distribution. Since it's a noise distribution, initially my fake nodes would be easily detected by discriminator. But later what happens is I will change the distribution. I'll slowly understand where I'm committing my mistake in creating a fake node and then try to update my distribution. And from this updated distribution, I'll be able to get much more smarter fake nodes. Okay, so till the time that you can fool discriminator, the network keeps on running. Okay, so this is the main theme. Now let us focus on more details. Actually, I have 8 to 9 minutes. I want to take extra time because this is the last class and I have to upload recorded videos, 1 or 2, maybe 1 mostly. So now let us understand, this is the theme of GANs, but let us understand the network of discriminator and then later we'll understand the network of generator also. Okay, so actually the discriminator network is a CNN. When I say CNN, maybe I'll apply sequence of convolution layers and its convolution depth would keep on reducing. Okay, you know that, right? So size of the convolution, the width and height would keep on would keep on reducing. And finally, the last layer is connected to fully connected layers, and finally it can tell whether it's a node is a real or a fake. Now, what about discriminator network? Sorry, what about generator network? Generator is also CNN, but it's a different inverted CNN. It is called inverted CNN. CNN inverted or inverted CNN. Why I have to go with inverted CNN? What is inverted CNN? I start with a small convolution size. I slowly increase. Why I have to go with inverted CNN? Because I have to generate a image which is having these dimensions. If I just print this, for example, if I just take this as a generator, I would get this image. That means I will get a small version of my fake node. I don't want, if my fake node size is this, my last layer also should have the same sized output. That means here, if my fake node size is 100 cross 100, so if the final layer in my inverted CN is also 100 cross 100, I can directly print it. Okay, so that's the reason I start with a random noise, slowly improve, and I get a final node size. The final layer will have the size equal to the image size. The final layer size in your inverted CNN is equal to the output image size. That's the reason we have to invert. So generator is basically same CNN, but the layer size increases rather than decreasing. That's all. Okay, fine. That's the main theme. Then actually, how do I increase? Okay, sir, you're telling that we have to increase. How is it possible? Generally, after convolution, the size will decrease now. And here also we apply convolution only. Sir, after applying convolution, the size will decrease. Sir, how can you increase the size? That's a question. The answer already you know that. The answer for this is upsampling. We have to upsample it. Again, upsampling, you know, for example, if I have 1, 2, 3, 4, if I want to upsample these pixels by a factor of 2 cross 2, then I'll be doing like this: 1, 1, 1, 2, 2, 2, 3, 3, 3, 3, 4, 4. That's all. This is my upsampling approach. So that means after convolution, your width and height would reduce, but I will perform appropriate upscaling or upsampling to ensure that I would get a final output sized layer which is equal to the real image width and height. Till that point, I do upsampling followed by the convolution layers, convolution operations. Okay. Now this is one angle, but let us understand more about slowly we're trying to build up the story here. So the next part is discriminator. Again, we'll come back to the discriminator once again. Now, discriminator, what it does is it takes fake data. It takes fake data from generator You know, it takes real data, which is there from the data set. It takes both. This both are fed to the discriminator. Now, what is its responsibility? The discriminator, what it has to do? It has to say whether it's 0 or 1, whether it's a fake or real. For example, if it's not able to do it, maybe classified real image as fake or fake image as real, then what it has to do? It has to go with backpropagation and update the weights. Update the weights. Maybe I passed 100 images, out of which 50 are fake and 50 are real. So if the discriminator could classify all of them as 50 of them as fake, 50 of them as real, that means the discriminator performed with 100% accuracy. It's like regular classification only. It's nothing great here. I just pass two classes of images, class 1 and class 2 images, and I just want to see whether the discriminator, traditionally CNN, just a CNN, can classify all those from individual classes or not. So the image that was generated from C1 has to be classified as C1. The image that is supplied from C2 has to be classified as C2. That's all. Dead simple. But the generator part is little different here. Generator part is little different. Let me say that now. Actually, you start with some random input vector because you don't know how to generate the fake guys. So let's start with the random input vector. This random input vector keep on changing. So till the time that I can fool the discriminator, this input vector keep on updating, and keep on updating. So it's generator. I'll be giving this to generator. And generator image, which is basically a fake image, is sent to discriminator. Sent to discriminator, and this discriminator would again classify it as 1 or 0. If this fake image is classified as 0, then I would update weights. If this fake image is not classified as 0, it is classified as 1. There's no point in updating weights because generator can fool the discriminator. So you need to do updating of your weights till the time that you can fool the discriminator. Once you fool the discriminator, then you can stop updating the weights. Of course, it's not for one epoch or one image. It is done across all the images, okay, and in multiple epochs. So this is for the generator part. Now, what is the loss function? See, we are done with the architecture, Nana. We are done with the architecture. We are done with the architecture. So now, if I just want to redraw the architecture, let me redraw the architecture also. Actually, we don't have time. Okay, so actually, one thing I just want to tell you, and maybe I'll stop at this point. Once the architecture is there, the next thing is, oh my God. Once the architecture is there, the next thing is the loss function. Actually, again, I'll reiterate, redraw the architecture, but the loss function I want to know. See, the loss function for this is actually mean max of expectation of log d of x plus expectation of log of 1 minus d of g of x. Again, this looks complicated, but this is dead simple. Even the proof that I'm going to tell is very, very interesting. Very, very interesting proof. It will not like be a proof. It will be very, very interesting proof. Maybe in the recorded video, what I do is I'll be sending you the explanation how we got this and other variants of GANs, because we just gave you the intuition and everything. So in the next recorded video that I'm going to send, we'll have all the details and covers the remaining part of the syllabus. Maybe it will be for 1.5 hours. So maybe by tomorrow, I'll try to upload tomorrow or day after tomorrow morning. I'll try to upload. Okay. Meanwhile, you complete the remaining syllabus of I think 5.5 units. We are done 5.7. We completed. Hardly we have to just complete this 5% syllabus, which is from GANs. So it will be done. Okay. So that's all for the day, and I think we'll meet tomorrow for the discussion. Okay, now let me just take your questions. Where is this? Where is here? Oh, where is? Are you there, guys? Okay, fine. So Shiva, are you there?
Yes, sir.
Okay, so not only Shiva, I think this would be the officially last class for this semester. Maybe I don't know what subject I'll take in the next semester, and we'll meet or not. We'll see based on the subject that you take and based on the subject I take. So if you have any questions with respect to anything, just ask me. I think you don't have time, but try to ask if you really have questions. Otherwise, tomorrow when you have a meeting, also you can ask. Any questions, Gautam, Shiva?